Hello there. This is our first lecture on what are called Turing machines, and these are the new devices that we will be talking about for the remaining 4 lectures, basically. These machines, these Turing machines, are very powerful, and everybody thinks that these are equivalent to algorithms, a general algorithm. So by the end of this lecture, you should be able to do the following: to formally and informally describe a Turing machine, determine the outcome of running a Turing machine on a given string, design simple Turing machines. Then you should basically be able to do all these things again, but for what is called the multi-tape Turing machine. And then you should be able to transform a multi-tape Turing machine to a single-tape Turing machine, right? You show that for every multi-tape Turing machine, there's an equivalent Turing machine with a single tape. Now, to talk about the Turing machine, we need to talk about the inventor of that machine, Alan Turing. And Alan Turing lived between 1912 and 1954, and he wrote the paper in which the Turing machine appears for the first time in the year 1936. Of course, in his paper, he didn't call it the Turing machine, but it came to be known by that name later on, of course, due to Turing. Now, Alan Turing did other things, and he is one of the major founders of computer science. And here are just 4 of his major contributions. The first one, which we will see, is what is called the Turing machine. And that's an automaton, as we will see. It's pretty much like the DFA or the PDA, but with a little bit more power, and just a little bit to make it as powerful as any general purpose computer, as we will see. So it's an automaton that is capable of performing any computation that could be described by an algorithm. We will never prove this, but that's basically what is called thesis. It's called the Church-Turing thesis, that algorithms are nothing other than Turing machines. The second contribution, which we will also see, is something called the Universal Turing Machine. And this is a Turing machine that takes as input descriptions of other Turing machines, kind of strings that describe other Turing machines. And then that Universal Turing Machine will take that description and basically simulate Turing machines given by the description. And if you think about what that is, that's basically what a computer does. So a computer is nothing other than an algorithm, right? This hardware machine that we all use is nothing other than a very simple algorithm. And it's the algorithm that goes fetch, decode, execute. Fetch an instruction from memory, decode it, then execute it. You just keep on doing that, right? But then, depending on the different instruction that you load in memory, the computer behaves differently, right? So it can display pictures, you can use it to do word processing, you can play a game with it, right? You can kind of browse the internet, you can do lots of things depending on the particular set of instructions or the particular program that is loaded into the memory of the computer. So that's basically what the Universal Turing Machine is. It takes as input, you load it with the code, the description of another Turing machine, which, as we said, is pretty much an algorithm, and then it kind of behaves the same way. So this was the first serious consideration of the idea of a stored program, the idea of storing a program as data and then using that data to behave in different ways. Third contribution is breaking the code, and if you have seen the movie The Imitation Game, which is about Alan Turing, I guess that this is what they highlighted there. So Turing developed a system to break the code of messages that were ciphered by the German Enigma machine in World War II. And in a way, Turing was also a person who was working in cryptography, not only in theoretical computer science, but also in cryptography as well. And the last contribution that we will mention is what is called the Turing test for machine intelligence. And this is a test that Turing proposed to use in order to decide whether a computer or a machine in general is intelligent or not. And in a way, Turing machine has been the first AI researcher, if we take that to be a contribution to AI, which indeed it is. So let's talk about the Turing machine itself. The Turing machine, just like the DFA and the PDA, consists of a finite control So it has finitely many internal states, and at any time it's in exactly one of those states. It has a tape which is infinite to the right, so the tape has a beginning and has no end. So far, this is exactly the same as PDA and DFA. And there is the head. Remember the head? But the head of the Turing machine is actually what gives it its power. Now, the major difference between Turing machines and the other devices that we talked about so far is that the Turing machine's head is a read-write head. So the Turing machine can write on its tape, right? So it's no longer just an input tape where the input is recorded. This tape can be used by the Turing machine to store things by writing them down on the tape. Okay? Now, if this is the only thing, then the Turing machine is no more powerful than a DFA, all right? However, we will see down here that there is something else about that head that gives the Turing machine the real power. Now, the Turing machine can both read from the tape and write on it. So the tape is some kind of an infinite memory. The first input symbol is placed on the leftmost tape square, as usual. And the head starts at the leftmost square, as usual as well, and can freely move to the left or to the right. Now, that's the real power, right? So the head of the Turing machine can write on the tape, but it can go back as well. It can move to the left. It doesn't just move to the right, like the head of the PDA and the DFA. And that's really the main aspect of the power here, right? Because if the Turing machine head can just write and then move on to in the right direction, that is, then it will never be able to go back and read what it stored, what it wrote earlier. But because the head can move to the left, it can do that, all right? So these things that it writes on the tape are really useful because it can go back and read them again. If the head is at the leftmost end of the tape, at the beginning of the tape, then if the Turing machine attempts to move the head to the left, the head will stay in place, right? It just gets stuck if it tries to move to the left, where it's already at the leftmost cell. The Turing machine accepts a string by entering a designated accept state. So there is one and only one accept state of the Turing machine, and once it enters that state, it halts. It stops its operation. It just stops. The machine rejects a string by again entering the one and only reject state. So Turing machines, unlike DFA and PDA, have a designated reject state. Each Turing machine has a single reject state, and if the Turing machine wants to reject, it enters that state, and once it enters it, just like the accept state, it will halt, it will stop. Now, if the Turing machine never enters the accept state or the reject state, it basically will run forever. It will never halt. It will keep on running and running and running, okay? So another thing that is kind of a little bit different here is that if you remember the head of the DFA and the PDA, once it reaches the end of the input, the device just stops, the automaton just stops. But for the Turing machine, this is not kind of reasonable because the Turing machine can keep on writing on the tape. So the head can keep on moving beyond the input and writing stuff on the tape, okay? So unlike a DFA, for example, where the DFA will stop exactly when the head reaches the end of the input, the Turing machine can halt by either entering Q accept state, or Q reject state. And it doesn't have to reach the end of the input. It can just start, move the head once, and the input is 1 million symbols long, move the head only once, and then halt, right, by accepting, for example. Or it can move beyond the input, it can read the entire input, continue moving to the right, writing other symbols on the tape, and then at some point it will reach a state in which it will decide to accept or reject, and then it will halt. Or it will be just run forever. So let's immediately apply our knowledge, this informal knowledge of what Turing machines do, and try to recognize this language, W#W, where W is a binary string. Now, this language is not regular, and it's also not context-free, although we didn't discuss the pumping lemma for context-free languages. But if you see it, you can use it to prove that this language is not context-free either. So it's neither regular, it cannot be recognized by DFA, and it's not context-free, it cannot be recognized by a PDA. So let's see if a Turing machine will be able to do it. So W hash W, the string to the left of the hash is identical to the string to the right of the hash. So let's imagine that this is the input, right? Suppose that that's the tape, that's the beginning. You have 0, 1, 1, 0, 0, 0, that's W, then the hash, and then 0, 1, 1, 0, 0, 0, that's the other W. And then this is the blank symbol. And the rest of the tape cells are filled by that symbol, this blank symbol, right? So once you see the blank, you know that that's the end of the initial input. So that's the input, and the head starts out pointing at the very first cell. So this is what we will do. Turing machine will look at that symbol, all right, and say, that's a 0. Let me overwrite it with an X. You're basically crossing the 0, right, by writing an X in place of the 0, writing an X on that cell, which will erase what was there and just end up with the X there. Then move one step to the right, okay? And then continue moving to the right, all the way to the right until you find the hash, and then you go to the symbol after the hash. Now, is this the same thing that you saw at the beginning and you replaced with an X? Yeah, that was a 0. So you basically replace this 0 with an X. Then that was a 0. So you basically replace this 0 with an X. Then move to the left, keep on moving until you find the X. So you're back here. Then move one step to the right. Now what is this? This is a 1. So let's remember that there was a 1 here and erase it, overwrite it with an X. Then continue moving all the way until you find the hash. Then go until you find something other than an X. That's a 1. So what will you do? You'll listen, is that the same thing I saw there? Yeah, it is. Then you replace this with an X, okay? And you continue going back and forth. You go back until you find this X, go one step, that's a 1. So keep on looking until the hash, skip all the X's until you find the 1. Yeah, that's the same symbol, replace it with an X. You keep on doing this until every symbol gets replaced with an X, right? So imagine at the time when this 0 gets replaced with an X, you're gonna go back, all right, all the way, skip all these X's until you find the hash, and then you find the first X. That's the first X. You go one step to the right, yep, that's the hash. So there are no more 1s and 0s to the left of the hash. Then you know that you're done with the string that appears to the left of the hash. Now, in order to make sure that it's identical to what's there, you really just need to make sure that there are no more symbols left at the end. So the head will move all the way across the hash, across all the X's, and checks the next symbol. If it's a 0 or a 1, that means that this thing is longer than that, then you reject. But because it's the blank, then you know that that's it. These two strings indeed passed the test. They were identical, the two strings across the hash. And then the Turing machine will enter the accept state and accept. So this is the description of what we just said. Turing machine will zigzag across the tape to corresponding positions on either side of the hash. If the two positions do not contain the same symbol, or if no hash is found, right, you have to have hash, then the Turing machine rejects. If both positions contain the same symbol, we cross them off by overriding them with an X. When all the symbols to the left of the hash have been crossed off, right, you check for any remaining symbols to the right of the hash. If there are any symbols, of course, after the X's, they reject. If there aren't, in that case, we accept, as we saw in the example. Okay. So let's look at a more precise definition of what a Turing machine is. A Turing machine is a 7-tuple, so it's made up of 7 things. Q, sigma, gamma, delta, Q0, Q accept, Q reject. Now, as always, Q is a finite set of states. Sigma is the input alphabet. Basically, this is the set of symbols that can appear on the tape as input initially when you start the Turing machine. And this alphabet does not contain this special blank symbol, because we need to sometimes we need to know where the input ends, all right, as we saw in the previous example. So you'll know that when you see the blank, which fills the rest of the tape cells that are not filled by the input. Gamma is what is called the tape alphabet, and this is the set of symbols that are allowed to appear on the tape, So it has to contain everything in sigma. So sigma is a subset of gamma because any input symbol is allowed to appear on the tape. And of course it has to contain the blank because the blank is already on the tape, right? And it contains other things like the X, for example, in the previous case, in the example that we looked at before. Now I'll come back to delta. Let's first look at Q0. As always, this is the start state. Q accept is the one and only accept state, which we said once the Turing machine enters, it halts and stops. Q reject is the one and only reject state, and it's different from Q accept. Now, what is delta? Delta is, of course, the transition function. And for the Turing machine, the transition function takes two inputs, a state and a tape symbol. And if you imagine what these are, they're just like for the DFA. This is the current state of the Turing machine, and that's the symbol the head is pointing at. And what does it give us back? It gives us the next state, and it gives us the symbol that the Turing machine will write. So on every transition, the Turing machine will write something on the tape cell that it is looking at. Now, if it doesn't want to write, if it basically wants to leave that symbol by itself, it just writes the same symbol, right? But in general, it just writes something. And then it moves, and it can move either to the left or to the right. So this L and R means basically indicate the direction of movement of the head. So the Turing machine will enter some state, will write something on the tape, then after writing, it will either move to the left or it will move to the right. All right, now what we need to do, as we always do, is to define the language of a Turing machine, and that is based on the definition of what it means for a Turing machine to accept string. Now, we will need some setup to get to that definition, but surprisingly enough, the definition here is much simpler than the corresponding definitions for PDA and NFA and GNFA, for example. A configuration of a Turing machine describes three things: its current state, the state of the machine, the current tape contents, the entire thing that is written on the tape, the entire string that is written on the tape from the beginning up to the first blank, and the current location of the head and where the head is. This is everything that you need to know about the Turing machine at any given time, right? This configuration. What the state is, what's written on the tape, and where the head is. So there is a kind of a string representation of a configuration that we're going to make use of again and again. So if Q is a state, and U and V are tape strings. Remember, gamma star is the set of strings over the tape alphabet gamma. Then if Q is a state and these two, U and V, are strings over the tape alphabet, then we write U, Q, V to denote a particular configuration. So if you look here, this string is basically a tape string, a state, then another tape string. And this is used to denote a configuration. Now, which configuration? A configuration where the current state is Q, this thing in the middle, and where the tape contents, what's with its string on the tape, is the string UV, the concatenation of U and V. So UV is whatever is written on the tape, and the position of the head is at the first symbol of V. So we basically use the state to indicate where the head is. So this is what's on the tape, and the head is at the very first symbol in V, so we just put Q right there. Now this is an example. So suppose this is the configuration of the Turing machine. It's in state Q7. This is what's on the tape, 1 0 1 1 0 1 1 1 1, and then that's the blank. And this is where the head is. Then you can indicate this by this configuration. So U here is the prefix just before where the head is, 1 0 1 1, right here. That's U. Then you put the state, Q7, then you put V, which is the remaining part, 0, and then the 4 ones. And the head is pointing at the 0, at the first symbol of V. Now, when V is the empty string, right, then the head is scanning the first blank after U, right? So if the head is here, for example, then this will be U, and V will be the empty string. If U is the empty string, then basically the head is at the leftmost cell of the tape. Here are some special configurations of Turing machines. So suppose we have a Turing machine M. The start configuration of M on input W is this configuration, Q0W. Q0 is the start state. W is the input, it's what's on the tape initially, and of course initially the head is pointing at the first symbol of W, so U here is the empty string and V is W. An accepting configuration of M is any configuration of this form, any configuration which the state is Q accept. This is called an accepting configuration. And similarly, a rejecting configuration is any configuration in which the state is Q reject. A halting configuration, which means a configuration which we know that the Turing machine has halted, is an accepting configuration or a rejecting configuration. Because remember, we said that once the Turing machine enters Q accept or Q reject, it halts. It stops, basically. Alright, so suppose that now we have two configurations of some Turing machine M, C1 and C2. Then we say that C1 yields C2 if M can basically move from configuration C1 in one transition into configuration C2, if it can change its configuration from C1 to C2 in one step, in one transition only. That's basically the intuition. Now let's make this more precise. Suppose that Qy and Qj are two states, A, B, and C are tape symbols that can appear on the tape, right? Not necessarily in the input, but they can appear on the tape, right? And U and V are two tape strings. Then we have basically two cases. The case where M would change from C1 to C2 by making a transition in which the head will move to the right, and the other case in which we'll change the configuration from C1 to C2 by making a transition where the head will move to the left. So A2 by making a transition where the head will move to the left. So if we have the following, if this is C1, that's the initial configuration, all right? So let's look at that. This basically means that what's on the tape is UABV, right? You look at it here. This is U, this is a string, right? Something before this symbol A. Then you have UA followed by the symbol B followed by some string V, right? Before the first blank. Okay, so that's what's on the tape. And the state is Qi, and the head is at that B, right? At the first symbol after the state in the configuration, right? So this is basically the configuration described by this. Now, if the transition function says that in state Qi, reading a B, right, which is the situation here in this configuration, then the next state will be Qj, right? So you need to enter Qj, write a C in place of the B, and move to the right. If that is what delta says, and we are in this configuration, then definitely this will be the next configuration. Now, what is this? So you have on the tape UACV, right, which is right here, UACV. And if you look at what happened, just the B changed to a C, all right? And the state changed from Qi to Qj because that's what the transition function says. And the head moves to the right, so now it's at the, it just moves to the right, one step to the right over here at the first symbol of that V, right? So that will be the new configuration, all right? So if you go from C1 to C2 by moving to the right, then this will have to be the case. This is the general pattern of C1 and C2 and the transition function. On the other hand, if the movement is to the left, then once again, you start in C1. This is C1, right? State is Qi, the tape has UABV, and the head is at the B. Now, if the transition function says in Qi reading a B, you enter Qj, write a C, and move to the left, then this is what should happen, right? The state becomes Qj, the B will be overwritten with a C, but then the head will move to the left. So now it's pointing at that A. And then if you want to represent this configuration, it will look like that. You have U, then you have Qj, right, immediately before where the head is, which is this A, then you have ACV, all right? So that's basically what it means for one configuration to yield another. Now we are ready to define the language of a Turing machine. So first, as always, we say what it means for the Turing machine to accept a string. A Turing machine M accepts input string W, if there's a sequence of configurations C1 through Ck. And before I tell you properties of that sequence, there is one thing to note, which is that if you remember, in all the previous cases when we defined what it means for an automaton to accept a string, there was always a relationship between the string, the length of the string, and the length of kind of the accepting sequence of states, right? Or sometimes we had to kind of say, okay, we're going to represent the string by adding some epsilons, and then that new thing will have a certain length, and it's related to the length of the sequence of states that the device will go through. But in the case of a Turing machine, there is no relation whatsoever in general. Because of what I said at the beginning, remember that the Turing machine may stop and accept without reading the entire string, so it doesn't have to go through a number of states, which is 1 plus the length of the input, and it may actually read the string and continue moving, continue making transitions beyond that input string, right? Because the head can just move, keep on moving and writing, keep on moving to the right and writing things on the tape. So this K is in general unrelated to W, right? The only thing is that, of course, it's finite. So to accept a string, the Turing machine will have to enter Q accept and halt, and in that case, there are finitely many configurations that it will go through. Okay, so what are the restrictions on that sequence? So as always, C1, the first configuration in the sequence, is the sequence. So as always, C1, the first configuration in the sequence, is the start configuration of M on W, is basically Q0 W. And of course, CK is an accepting configuration. The last configuration is one in which the status Q accepts. And for any pair of consecutive configurations, Ci and Ci plus 1, it must be that Ci yields Ci plus 1. That is, the Turing machine can change its configuration from one configuration to the next in the sequence by basically observing and respecting the transition function. Then the language of a Turing machine, N, or L of M, is the set of all strings W over the input alphabet that M accepts. And we also say that L of M is the language recognized by M. Okay, so let's go back and remember what we said. We said that when you run a Turing machine on some input, three things can happen. It can accept the input by entering Q accept and thus halting, or it can reject the input, and the only way it does that, you have to take care, the only way the Turing machine can reject an input is by entering Q reject. And of course, once it enters Q reject, it will halt. The third thing that happens is that it loops forever. It never enters Q accept, and it never enters Q reject, and therefore it loops forever. Now, looping forever is neither accepting nor rejecting. You have to understand that. Reject here for Turing machine has a very for Turing machines has a very specific meaning. It means that the Turing machine enters Q reject and stops. All right, but looping forever is not the same as rejecting. Now, Turing machine accepts a string by entering Q accept and halting, but it may not accept the string by doing one of these two, right? So when we say the Turing machine does not accept a string, we either mean that it rejects it or that it loops forever on it, okay? Now, machines that do not loop forever are of course preferred. We like them more. Now, why is that? The reason is the following. Suppose you have this Turing machine, you give it an input, and you run it, and it keeps on running, right? Keeps on moving, the head keeps on moving, writing things on the tape, going back and forth on the tape, and you wait and wait and wait for years and years and years, and it's still running. Now, what does that tell you? Is this string in the language of the machine or not? Actually, you cannot tell, all right? You cannot tell because you do not know what happens, right? Even if it takes millions of years. You cannot decide just by that, but it's taking a long time, that the string is not acceptable, right? That the machine is running forever. Actually, you never know that a Turing machine is looping forever. If you're just watching its behavior from the outside, if you don't look in the inside, if you don't look at the transition function, you would never be able to tell that the Turing machine is running forever on a certain string. And This way, you will not be able to decide for that string whether it's accepted or not by the Turing machine, all right? You really cannot tell whether it's accepted or not. You cannot tell whether it's in the language of the machine or not. So those machines, all right, that may loop forever on some inputs, right? And of course, in that case, they say they do not halt on every input, are not preferred. Now, on the other hand, Turing machines that never loop forever on any input, that halt on every input, are definitely better because given any input, even if it will take a lot of time to give you an answer, it will give you an answer. It will either accept or reject. It will stop and you will know whether it accepted or rejecting, right, by looking at the final state it reaches. So those machines that halt on every input are called deciders. Deciders because they always decide. They decide their languages. Given any string, if it's in the language of this machine, it will accept, and if it's not, it will reject, and you would know if you wait long enough. But if the machine is not a decider, if it runs forever on some inputs, then it does not decide its language, right? Basically because there will be strings not in the language on which it will run forever, and for those you will never be able to tell whether they are in or out. Okay, we say that a language is Turing recognizable or recursively enumerable, or just RE, if it's recognized by some Turing machine. Now, what does it mean to be recognized by a Turing machine? It means that there's a Turing machine that accepts every string in the language and does not accept every string not in the language. But by saying that it does not accept strings not in the language, we are basically saying that it either rejects the string if it's not in the language, or it runs forever on it, okay? So this notion of Turing recognizability of being recursively enumerable just means that there's a Turing machine that accepts every string in the language and does not accept strings outside the language. Maybe it runs forever on some of them. But a language is Turing decidable or recursive if there's a Turing machine that decides it. Now, what does it mean for a Turing machine to decide a language? It means that it accepts every string in the language and rejects, by entering QReject and halting, every string not in the language. So if we have a language recognized by a Turing machine that never runs forever, then it's also decided by that Turing machine. Now, you should note that all Turing decidable languages are Turing recognizable because deciding is a special case of recognizing. You decide if you accept or reject and never run forever. You recognize if you accept, reject, or run forever. But of course, as we will see in our last lecture, it's not the other way around, which means that there are languages that are RE but not recursive, that are Turing recognizable but not decidable, which means that for these languages, there are Turing machines that will accept every string in the language, but will reject or run forever on strings outside the language. But for this same language, there is no machine that will accept every string in the language and reject every string outside the language. For those languages which are called undecidable, there are strings on which any Turing machine recognized in the language will have to run forever. So let's look at more examples of designing Turing machines. Suppose we want to design a Turing machine which will recognize this language. What's the language? 0 to the 2 to the n. Now, what does that mean? It means strings of zeros whose length is a power of 2, right? Where n is 0 or more. So the shortest string here is 0, then 0, 0 when n is 1, then 4 zeros when n is 2, then 8 zeros when n is 3, then 16 zeros when n is 4, and so on. So here's kind of the idea of how we will do this, right? Basically, you would like to check if a given number, right, is a power of 2, right? Because basically the length of the string is a number and you would like to check if that number is a power of 2. So how do you do it? Now, if you're using Python or Java or any high-level programming language, one idea is to keep on dividing the number by 2, right? So if the number is 16, for example, you divide it by 2, right? And then you check the result. Now, first of all, you take the number, you check if it's even, right? You check it's the remainder dividing it by 2. So 16 is even. Then you divide it by 2, okay? You get 8. You check if 8 is even. Yes, it is. Then you divide it by 2 again. You get 4. You check if 4 is even. Yes, it is. Then you divide it by 2 one more time. You get 2. Now you check if 2 is even. It is. Then you divide it by 2. You get 1. Is 1 even? No. But because it's 1, because you ended up at 1, then you accept. Then 16 is a power of 2. Now if you try it with, let's say, 12, for example, which is not a power of 2, is 12 even? Yes. Then you divide. You get 6. Is 6 even? Yes. Then you divide. You get 3. Is 3 even? No, it's not even, and it's not 1. 1 is a special case. 1 is 2 to the power of 0. 1 is the only power of 2 which is odd, right? So for this case, when you reach 1, you accept. But 3 is an odd number, which is not a power of 2, then you stop and reject in that case. So that's what we want to do. We want to take this number and divide its length by 2. Keep on doing that so long as the length is even. But it's not easy to do this with a Turing machine, of course. So we're going to do it in an interesting way, right? So suppose you have that input string, which is 8 zeros. We should accept it, all right? Then here's what you do. You skip the first 0, and you go to the second, and you cross it off. Replace it with the X. Then you skip the next 0, and you go to the next one, and you cross it off. Then you skip, cross, skip, cross, right? So every other 0 is replaced by an X. Okay, now you're done with that. Then you go back at the beginning, and you start all over again. You skip the first 0, then look for the next 0, this one, you cross it. Then you skip the next 0, here it is, you look for the next, for the following 0, which is this one, then you cross it. Done. Okay? Do it again. Go back here. You skip the first 0, look for the next one, which is this, you cross it. Then you go, no more zeros. Then you go back, right? Here's a 0, right? At the beginning you skip it, and you keep on looking for a matching 0 and you don't find any. But you ended up with a single 0. Then you accept, right? So if you look at what's going on here, every time we're dividing the length by 2, right? So we started with 8 zeros, now we have 4, then 2, then 1. And because we reached 1, we accept it. Now let's try to do it with the wrong string. So this is a string with 6 zeros, which is not a power of 2. So you do the same thing again. You skip the first 0, you cross the next. You skip, cross, skip, cross. Okay, done. Do it again. Go back. So you're gonna skip, cross, skip, no 0 to cross. So you found the 0 and you didn't find a matching 1 to cross, which means that the number of zeros is odd. But it's not 1, and for that reason we reject in this case. So that's basically the idea. So here's how this Turing machine will work. You move from left to right, crossing off every other 0. If in that step the tape contained exactly a single 0, then you accept. However, if in that step the tape contained more than a single 0, but the number of zeros was odd, then you reject. How do you know that it was odd? By basically skipping a 0 and not finding a 0 to cross off. Okay? Then you reject. Okay? When you're done with this, you return the head to the left-hand end of the tape, then you repeat this again. Okay? Now, of course, if you look at this Turing machine, it will definitely halt at some point, right? You will either reach a single 0 on the tape or an odd number of zeros on the tape other than 1. And in that case, you will either accept or reject, so it will never run forever, and therefore this machine decides this language. Now let's look at some details, right? How we're going to implement them at the level of head movement of the Turing machine. How are we going to cross off every other 0? How will the Turing machine know that I now need to skip or to cross? Now it will do that using the finite control, using the states, right? So basically, just like we used to do with DFA, there will be a state or a bunch of states, all right? So that when the Turing machine is in any of those states, it will know that now I'm moving the head and I'm looking for a 0 to skip, all right? So once it reaches a 0 and it's in one of those states, it will not touch it. But then it will switch the state, all right? And it will enter another state and maybe another whole group of states, right, to aid with the head movement, where when it's in one of those states, it knows that the next 0 that we'll find will need to be replaced with an X, all right? So using the states, the Turing machine can remember those things, can remember whether it's looking for a 0 to skip or a 0 to cross off. How will it know that the number of zeros is odd? Now that's easy, right? The number of zeros is odd if I'm in one of those states where I'm looking for a 0 to cross and I don't find a 0, right? Then the number of zeros is odd in that case. And how will I know that it's one in particular? Yeah, that you need to distinguish. So you will need to distinguish between whether you are looking for a 0 to cross because you found a single 0, or you're looking for a 0 to cross and you found more than 1 0 before, right? So again, you can do this. These are finitely many distinctions, and you can make those distinctions using the states. Okay, how will the Turing machine move its head all the way to the beginning of the tape? Remember, the head of the Turing machine can move to the left. However, what we said is that if it reaches the beginning of the tape and it moves to the left, it will stay in place, but it will never know that. Just like with the PDA, remember the PDA does not know that the stack is empty. So there are several ways, there are several things we can do in order to kind of let the Turing machine know that it reached the beginning of the tape. And one way to do it, which is the simplest actually, is to, from the beginning, shift the whole string one square to the right and write a special symbol at the left end of the tape. Let's say the $sign to mark the beginning of the tape, right? You can do that, okay? Now, one thing that I want to say is that we will not be drawing state diagrams for Turing machines. And the reason is that in many cases, the Turing machines that we will be discussing will be quite complex, all right? Complex, they're really easy to describe in English like we did here, but to draw the state diagram, it will be a lot of work and it will be very tedious. So we will content ourselves by a high-level English language description of the operation of the Turing machine as we've been seeing in the example so far. Here's one more example. We want to design a Turing machine which will recognize this language, a to the I, b to the j, c to the k, with the product of I and j is equal to k. All right? So you'd like to check if the product of the number of a's and the number of b's is equal to the number of c's. So this is the idea basically. So suppose you have that input string, which is a correct string, right? So you have 3 a's, 2 b's, and 6 c's. So 3 times 2 is 6. Okay. So first of all, we're going to shift the whole thing to the right and write the $sign at the beginning. Okay. Then you go, you look for an a, you found an a, you cross it off. Then you skip all the a's until you find a b. Then you replace the b with another symbol, let's say a y. Then you skip b's and you look for the first c. Yeah, you basically keep on moving to the right looking for the first c, you replace it with, let's say, capital Z. Now you go back, right, skipping all the z's and the b's until you find the y, then you go back looking for the first y. Once you find it, move one step to the right. Now is that a b? Yes, you replace it with a y. Then go looking for the first c, which will be this one, replace it with a z. Now go back for the first y, here it is. Move one step, that's not a b. Then we're done with the b's. Then what you do is that you kind of restore the b's, replace each y with a b, right? So you go back here, replace the y with the b, replace this y with the b, then skip all the a's until you find the first x, okay? Then move one step to the right. Is there an a? Yes. Then let's do it again. Replace the a with an x. Then go find the first b, replace it with a y, right? Then go find the first c, which is this, replace it with a z. So you match this b with this c, right? Y and z. Then you go all the way to the left looking for a b, replace that b with a y, go all the way to the right looking for a c, replace it with a z, right? So what are you doing now? With the first a, we crossed off 2 c's, and we made sure that there are we crossed off as many c's as there are b's. And with the second a, we did the same thing as well. Right? Now you're going to repeat it again. So you're going to go back, you find the y, then you go to the right, you will not find the b. So you go restore the y's, restore the b's, I'm sorry. Then you go to the left looking for an x. You will find this a, you're going to replace it with an x. Then you're going to once again match the c with every b that you have, which will work. And this, you will end up in this situation, right? You will end up with all the a's replaced by x's, the B is restored, and all the C is replaced by Z's. Then you're going back looking for an X, you'll find this one. Move one step to the right, that's not an A, so you're done with the A's. So the only thing that you need to make sure of now is there are no remaining C's at the end. So you basically move the head all the way to the end and make sure that there is a blank after the last Z. Now, that is the case, and it is the case here, that we accept. So this is the description of what we just kind of demonstrated. You mark the left end of the tape, as we saw with the $sign. Scan the input from left to right, just one time at the beginning, making sure that it's in the right form. It's some A's, one or more A's, followed by one or more B's, followed by one or more C's. The symbols appear in the right order. If they don't, then reject. If they do, return the head to the left-hand end of the tape. Now, if there is an A, and at the beginning there should be at least one A because we checked that there is at least one A, it's a plus, not a star, then cross an A off, replace it with an X. Then move to the right until you find the B. Then zigzag between the B's and the C's, crossing off one of each until all the B's are crossed off, okay? As we saw in the example. Now, if you run out of C's before you run out of B's, then you reject, all right? Because it means that AB is bigger than, the length of A times the length of B is bigger than the length of the C. The length of the A's multiplied by the length of the B's is greater than the length of the C's. So in that case, you reject. Otherwise, you restore the crossed off B's, all right? And then you go back to step 3, right? You turn the head to the left, look for an A. If there is an A, cross it off, and then you do this again. Now, this else is if you run out of A's. If you run out of A's, you go all the way to the end as we saw, making sure that all the C's have been crossed off. If they are, except if there are remaining C's, then it means that the number of C's is bigger than the product of the number of A's and B's. In that case, we reject. Alright, so this is fine, but it could be a bit tedious to work with the Turing machine to describe kind of simple computations like the one that we looked at now. So the thing is that the definition of Turing machines that we have presented may be varied in several ways, giving a kind of variance of Turing machines. So you can have multi-tape Turing machines, a Turing machine with more than one tape, non-deterministic Turing machines. And we will discuss these two. We'll discuss this today in this lecture, and the non-deterministic machines in the next lecture. You can have Turing machines with two-way infinite tapes, tapes that have no beginning and no end. And Turing machines with multi-track tapes. These are Turing machines where the tape is divided into tracks. So you can write in each cell finitely many symbols, and you can read finitely many symbols in one transition. A multi-head Turing machine, so a Turing machine with a single tape but with several heads, and each one of them is at a different place on the tape. Now, interestingly, all of those variants are provably equivalent to the basic standard Turing machine. Equivalent means that any language that is recognized by standard Turing machine is recognized by any of those variants and the other way around. So to prove that two Turing machine variants are equivalent, what you basically will need to do is to show that each one can simulate the other, right? And that's what we will be doing, right? We will look at two of those cases, the multi-tape machine and the non-deterministic Turing machine. A multi-tape Turing machine is very similar to the ordinary Turing machine, but with several and finitely many tapes. Each tape has its own read-write head. The heads independently move to the left or to the right, or they can also stay put, okay? So if you have multiple heads, it's easier if you may allow that some of them may not move at all, right? That some will move and the others will stay in place. You may be able to simulate this if you don't have the stay put option, but it will be very hard to actually describe that simulation. So with a multi-tape Turing machine, the heads have the option of not moving at all right? The input is initially on the first tape, right? Think of it as the bottommost tape, for example, and the rest of the tapes are initially empty, and the heads are all pointing at the very first cell of their tapes. Now, the only thing that we need to do in order to change the formal definition of the standard Turing machine to a K-tape Turing machine is to just do this. So delta takes K plus 1 inputs, the current state, and then K tape symbols. What are those? These are the symbols that are read by each of the heads on each of the K tapes. And it gives us back the new state, and it also gives us K tape symbols. What are those? These are the symbols in order that each head will write on its own tape. And then it gives us K of those symbols, L or R or S. L for move left, R for move right, S for stay put. And basically, for each head, the transition function needs to tell us on that transition whether it will move to the left, to the right, or stay in place. Now, the best way to understand multi-tape Turing machines is to use them in an example. So this is the same problem again. A to the I, B to the J, C to the K, where I times J is K, and all those are positive integers. Now let's do it now. Let's recognize actually a decider for this language using a multi-tape Turing machine. I'm gonna use 3 tapes. So initially, suppose we have this input, 3 A's, 2 B's, 6 C's, which is correct, and the other tapes are empty. Now the heads are pointing at the leftmost ends. So the first thing is, we're gonna kind of do an initial setup. So we're gonna leave the A's on the first tape, but we're gonna mark the start cell with the $sign, copy the B's to the second tape, and put the $sign here at the beginning as well, and copy the C's to the third tape. All right, so we have the $signs to mark the beginnings of the tapes. We have the A's on the first tape, the B's on the second, the C's on the third. Okay, what do? All the heads will move 1 step to the right. Now, this is an A, so we have an A here. So now you're at the beginning of the B's and at the beginning of the C's as well. So what the C's as well? So what do? You basically keep on moving the 2 heads, this head and that one, together in lockstep fashion, and keep this one in place. This one will stay put. And these will keep on moving together, and the Turing machine will just make sure that the second head is reading a B and the third head is reading a C, right? This will happen until the second head goes to this blank over here, and the third head goes to the third C. Now that we've reached the blank, what happens is that we move this head all the way to the beginning, right? We keep this head in place, and we move it then 1 step to the right, so it's right here, and we move this head 1 step to the right as well. Now there is another A, so you will need to kind of repeat what you did. So what do you need to do now to start moving head 2 and head 3 together? So you move this one. Now this is a B and this is a C. Fine. Move them to the right. If you move this to the right, you have a B here and a C here. That's correct. Move to the right one more time. So this head will actually be pointing here, and this head will be at the blank. Now because you reach the blank, you reset. You move the head all the way to the beginning and then 1 step. And then you move this head 1 more. You have 1 more A, you repeat again, all right? You keep on doing this until you finally will match all the B's with the C's, right? So you'll find pairs of C's basically responding to the pair of B's here until this head is at the blank. All right, then what you do is you will go down here, right? Remember the head was at the third A, you move it 1 step to the right. That's not an A. The only thing that you need to do is to make sure that that's indeed a blank and there are no more C's, and then you accept. Now, this algorithm is, I find it much simpler than the single tape one, because the head is not going back and forth really. All the heads are actually going to the right, except of course the second head, which needs to go back to start matching the B's with the C's all over again. But it's much simpler to describe, and that's the utility of having multi-tape Turing machines, because they simplify our lives when we're trying to describe complex algorithms. But that's about it. This theorem says that every multi-tape Turing machine has an equivalent single-tape Turing machine. That is, the multi-tape Turing machine is not really doing anything more powerful than the single-tape Turing machine. You can simulate it with a single tape, right? Now, the other way around is quite trivial, right? That for every single-tape Turing machine, there's an equivalent multi-tape Turing machine. Yes, of course, because a single-tape Turing machine is a k-tape Turing machine with k equal 1. That's basically what it is. Or even if you have a multi-tape Turing machine with 100 tapes, you will keep all the tapes, the 99 tape 2 through 100, you keep all the heads fixed, staying in place, and only use the first tape, right, to simulate a single tape Turing machine. Now, the other direction is the tricky one. And I'll first talk about how we will use a single tape to represent the configuration of a multi-tape Turing machine. So consider this example. This is a multi-tape Turing machine M with 3 tapes over here, and this is what's on the tapes and where the heads are. And this is a single tape Turing machine, and we will use its tape to represent the configuration of this machine. All right, so how are we going to do that? Now, because this one has 3 tapes, This one has on its tape 3 blocks, and each block is delimited by 2 hashes. So this is one block over here, that's the second block over here, and that's the third block over here. Now if you look at the symbols of the first block, you will find 0, 1, 0, 1, 0, which are exactly what you have here, 0, 1, 0, 1, 0. For the second, you have AAA. Here you have AAA. Then you have BA and you have BA. Now what is that dot? Now the dot basically indicates where the head is. So the head of the top tape is at that one. So you have the dot here. And here the head is at the third A. You have the dot on the third A. And here it's on the B. So you have the dot on the B. Now what is this dot? Nothing. This one dot is just one symbol. This is a symbol. So you have a 1 and you have a dotted 1. You have a 0, you have a dotted 0. You have an A, you have a dotted A. You have a B, you have a dotted B. So for every symbol of M's tape alphabet, we're going to have 2 copies in S's tape alphabet. The symbol itself and a dotted version of it. Whenever the head is at that symbol, we're going to indicate that by using the dotted version of the symbol. Alright. So let M be a K-tape Turing machine and S a single-tape Turing machine. S will simulate M using its single tape, as we described. K contiguous blocks on S's tape will correspond to M's tape, to M's K-tapes, and each block, as we saw, is delimited by 2 hashes. Now, to keep the track of the locations of the K-heads, S uses a single dotted symbol within each block. For every symbol A of M's tape alphabet, there is a symbol A dot in S's tape alphabet. And if a symbol A dot appears in the ith block on S's tape, then the ith head of M is pointing at that place and the symbol A, as we saw in the example. Alright, so here is the simulation. What we saw on the previous slide was how we will represent the multi-tape Turing machine on a single tape. Now this is how we're gonna simulate a single transition of the multi-tape Turing machine. So on input W1 through Wn, S will represent the initial configuration of M's tapes this way. So you have K blocks, right? Okay. Only the first block has the input on it, and the dot is on the first symbol because the head of M is pointing at this W1, and the rest of the tapes are empty. So in each of the remaining blocks on S's tape, you have the dot on the blank symbol, which means that basically the tape is empty. Now, to simulate a single move of M, S will scan its tape, this tape, from the first hash, from the very beginning, to the last hash. Why is it doing that? It needs to determine the symbols that are dotted. It needs to know which symbols M's heads are pointing at. So S will do a single scan of its tape, moving from the beginning. Okay, the dot here is on W1, keep on moving, it's on this blank, then on the third block, it's on an A, for example, and so on. All right? Now, when it's done, it needs to remember which symbols are dotted, and it can do that using its states again. It can enter a state, all right, that will indicate exactly which symbols are the dotted symbols, all right? So, for example, suppose that the Turing machine M has 3 tapes, as we saw in the example a couple of slides back, and that the first head is pointing at a 1, the second at an A, and the third at a B. So basically, as S will move its head looking for the dots in each block, once it reaches the end, it will enter a state, let's call it Q1AB, where the 1AB indicate the symbols that the 3 heads are pointing at. And because the number of possibilities of the symbols where the heads can be pointing is finite, because we have finitely many tapes in M, and because each tape and because the tape alphabet, being an alphabet, has finitely many symbols, then we need only finitely many states to distinguish between all the possibilities for where the heads of M can be pointing. Okay? So on a first scan, S will identify the dotted symbols. Then it will make a second pass on the tape where it will update the positions of the dots according to M's transition function. So basically, if M says, given the state that I'm in, and given what my heads are reading, I will write an A, or for example, I will replace the 1 on tape 1 with a 0 and will move the head to the right. Then S will go to the first block, replace the dotted symbol, the dotted 1, with a 0, and then replace the next one with a dotted version of it, okay? And so on, right? So basically, you can do that. Now, if at any point S attempts to move a dot rightwards onto a hash, now why would that happen? Suppose that the dot is here, for example, right? just on the symbol just before the hash, and M will make a right movement with its first head. So the head will need to move beyond that symbol. So it will go to the hash here. So to simulate this, S will need to shift all the tape content starting from the hash one step to the right, and then override the original hash by a dotted blank, because now it's moving to a cell that it has never visited before. So of course it's occupied by blank, and because the head will be there, then it will be a dotted blank.